Okay, this is Phys 2320 Computing 2, and this video is the fifth one in the Scipy series, and this is talking about how to use Scipy to solve differential equations. Okay, so often in physics we find ourselves in a situation where we can express a particular thing we're studying as a set of differential equations, but those equations are a bit too complicated to go and solve analytically, and instead you have to go and solve them numerically. So Scipy gives us some ways of actually going about doing that, but we have some constraints. So the way I'm going to show you using Scipy, you need to be able to express your system as a set of first order equations, that is in terms of dy dt is equal to some function of y. If you have more complicated problems, as I'm going to show you, you have to do a little bit of work first to get it into a format that's going to work with the Scipy functions. You also need to have suitable boundary conditions, of course, and in particular, for this particular method, you have to know what the starting conditions are. And then the other thing you have to be aware of course, is you're doing a numerical calculation, which means you're always subject to numerical accuracy. So you're not 100% guaranteed to get exactly the right answer out, and it's a question really of how accurate is accurate enough. And then the other thing you need to know is going to be evaluating the solution over a fixed range of points, so for a fixed set of times, for example. So you need to have some idea of knowing where it is you want to find your solution, what's the correct ranges of time to look at, and things like that. Okay, so I'm going to introduce you to the problem we're going to do as our example, and we're going to look at solving the oscillation of a rigid pendulum which isn't in the small angle limit and does have air resistance. So I'm just going to quickly run through the actual physics about what's going on. So we're going to try and figure out what angle this pendulum is making to the vertical. So in fact what we're going to do is going to work in an angular regime. So this is all using the angular mechanics from Physics 1. So first of all, you are going to have a moment of inertia. Because this is a uniform rod of a certain length L, then we can calculate its moment of inertia is 1/3 times its mass times L squared. So therefore you're going to have a torque, which is going to be given by that moment of inertia times the angular acceleration, and that torque is also going to be given then by the component of the weight that's acting perpendicular to the pendulum's length and is acting through the middle of the pendulum. So in this expression here, the mg sine theta is the component of the weight perpendicular to the pendulum, and a half L is the point through which that force is acting to give you the torque. And it's a minus sign because it's trying to restore the pendulum back to the middle. So that equation on its own would be a thing that would describe simple harmonic motion if theta was small. So normally you'd make the approximation that sine theta is small, and then you get a simple harmonic oscillator out. But we're not going to do that. We're going to keep the sine theta in there explicitly. And the other thing we're going to do is going to add air resistance. Now typically air resistance goes as the area of the thing that's moving times its velocity squared times a constant which covers both the drag, so the coefficient of drag, and the density of the air through which the thing's moving. So that's given down here. So what we have here is we have y times L. So y is the width in and out of the screen. So y times L is the area, the cross-sectional area. And then we've got eta as being the thing that's all the drags mixed up together. The 3 comes about because of the fact that it's moving around. One end is stationary and the other end is moving. It's moving in an arc. And then we have an L squared and an omega squared, which is basically the velocity, the linear velocity squared. But of course we want to work with the angular velocities, which is why we've pulled it out separately as omega squared. So, and then finally this omega hat is a unit vector that is simply just saying that the drag is trying to slow the thing down. So when the pendulum is swung out this side and is swinging in towards the centre, the drag is trying to slow it down. And that omega hat just takes care to make sure that the sign of this term is correct for whichever way it's moving. Okay, so we're going to take that. So there's our equation, and the first thing we're going to do is go and express everything in terms of theta, and do a little bit of rearranging. So we have to rewrite this equation in terms of d2 theta dt squared, and then the moment of inertia comes through, and you mess around with it, and your omega comes into a d theta dt squared, and this then becomes what looks like a differential equation that does not look very pleasant to try and solve analytically. It's going to be a bit of a pain to find some function that has going to handle the sine theta and the d theta dt squared there, which is why we want to go and solve this numerically. Now, the method that we're going to use can only go and solve things which are d something dt, but what it can do is solve a set of differential equations simultaneously. So what we're going to do is we can convert this from being one second order differential equation into a pair of first order differential equations. I'm going to do that by creating some new variables. So first of all, rather trivially, we're going to create a variable x1, which is just theta, and then we're going to create another variable x2, which is d theta dt. So now we can express this second order equation as two first order equations that looks like this. So the first one simply says that dx1 is d theta dt, which is x2. So x1 prime, so dx1 dt is just x2. So that's really just expressing what's given in when we created those variables. The second line says x2 prime, so dx2 dt, which is d2 theta dt squared, is, and then we've rewritten the main equation in terms of x1 and x2, and our omega hat is now just become an x2 hat. So this is what we're going to feed into our routine to go and solve the differential equation. And what we're going to do then is we're going to try and get solutions for x1 and x2 as a function of time. So to do that, we're going to make use of this function, the odint function that's in scipy.integrate. And as you see from its help page on the Scipy documentation, it's a fairly intimidating looking function. But as we're going to see, it's actually not too bad to go and use. It has lots and lots and lots of parameters, but most of the time you can ignore most of them. Okay, so the main thing we're going to have to do is going to have to write a function that is going to take in our variables, so we're calling them x1 and x2, and it should calculate dx1 dt and dx2 dt. So in other words, we've got to write a function that is going to do this sum for us. So given x1 and x2, it has to return then x1 prime and x2 prime. So in other words, it has to do this. Okay, so let's go look at the code to go and do this. So we start off at the top here. We're just going to do the importing the functions we're going to need. So some things from NumPy, the Scipy integrate ODEInt, the magic function we need, and then I'm going to show you the results by plotting them. So we need to import matplotlib.pyplot. Okay, the next thing we're going to do is we're going to set up those constants from our problem. So the length of the pendulum, the acceleration due to gravity, the mass of our pendulum, the distance of the pendulum extends the depth of it, or the distance in and out of the screen, and then finally our drag coefficient, which to some extent is a bit of a magic number for this problem. It's not easy to go and explain empirically why you get that, except it's to do with the coefficient of drag times the density squared. Okay, so what we have to do is we have to write our function that's going to actually express the system of differential equations. So I've called this function model, and this function takes in as its first parameter our x1 and x2 as an array. So it's going to feed x1 and x2 as an array. It's then going to take an array of times. It's going to take then a set of parameters which are our constants. And first thing we're going to do is going to unpack that variable x, which you see should be our theta and our d theta, so in other words our x1 and our x2. So I'm going to unpack those into theta and d theta. T's are times, and then these guys are all just the constants that we've had before. And then we're going to calculate f, which is going to be a list of two things, and those two things are the two rows of our equation here. So the first row is just x2, which is our d theta, and the second thing is going to be this row, which is the more complicated sum. Okay, so there we go. The first thing is just d theta, and the second thing is the sum we've got, the more complicated sum. So this is the bit that's the simple moment acting in the middle of the pendulum, and then this is the bit that's the drag. So minus sine d theta, that's our x2 hat, and then this is the rest of the expression there, and then we just return those values. Okay, so that's our model function. The next thing we need to have is we need to have our boundary conditions, our initial starting point. And we're going to start off with setting the initial value of theta, our x1 value, as pi by 4, so 45 degrees. I'm going to set the initial velocity at 0. So in other words, we're pulling this pendulum back to 45 degrees and then letting it go. We're also going to set a couple of things to do with solving it. These are basically how hard the differential equation solver is going to work to try and get a solution. And now we need to go and set some things up to do with how time we want to look at what the pendulum's doing over. So we're going to look at it for 10 seconds, and we're going to look for 1,000 points within those 10 seconds. So in other words, we're going to measure it every 10 milliseconds to see what it does. So we now just create a variable t, which is just an array of time. That's using the linspace function. And now this line here is the magic bit that does the work. So we've got the ODInt function, we've got the model that we're trying to solve it over, we've got our initial conditions, we've got our time, and then we're passing in this args keyword value, all of those constant parameters. And then finally we're going to pass these two things to do with the tolerances, how hard it's going to work. So that's going to return in sols an array which is got two columns and 1,000 rows. The first column is going to be our x1, which is our theta, and the second column is going to be our x2, which is our d theta dt. So then we're going to just plot them and show what it is. And that's all there is to it. So it's really just, this is the key bit, just writing this function that has to express those differential equations once you've done the hard work of putting them into linear equations. Okay, so we've run that code. There we go, and it produces a nice little plot. You see it's really quite speedy. So what you can see here is the blue line is the angle. So we're starting off at pi by 4, and you see it damps down over time, and the green is the velocity. If we wanted, for example, to go and say, well, what would happen if we started with it at its centre and we gave it a kick with a certain velocity? Well, that's quite easy to do. All we have to do is just change our initial conditions. So we change that from 0 to pi, say, so we're going to give it a kick of pi radians per second, starting from 0, and there you go, that's what happens. So you see it starts at 0 and it starts going up and oscillates again. We can try changing the damping. So if we change the damping by an order of magnitude, that's fairly extreme, and run it again. Oops, we've got the plot. There we go. Oops, I ran it twice. So you see now it damps much faster and comes down much more quickly. And you can also see what happens if we change the damping an order of magnitude the other way. So if we go from 7 to 0.7 and run it, there we go, and you see you get hardly any damping at all. So it's doing what you'd expect it to go and do. There's a little bit of damping. You can see that velocity is gradually getting smaller, but it's changed it quite significantly. Okay, and that's really all there is to going and solving differential equations using Scipy and Python. So, in summary, Scipy integrate ODInt is your friend for these sorts of problems, so long as you can write it as a set of first order equations, so creating new variables if you have to, and writing a model function that takes the variables and then it returns the variables at the given time. And it all just basically works.